Welcome to Engineering Class. Today, we'll look at choosing a route in a city for transportation, and we'll learn about integration and differentiation by choosing the route. So, if I ask you to choose a route, the blue route or the red route that we have mapped out on the city of New York, which one would you choose? Now, consider that I want to have the most cost-effective route. Now, what would you have to consider? Now, if each route costs the same per mile to build, then we could just say the decision would be based upon the length of the route. The shortest length would win because the length is proportional to the cost. What I mean by proportional, I mean there's a constant k times the length that will equal the cost. So to show you that this is the big problem in the transit world, you can see that cost per passenger mile is a big metric. So you have for light rail, it's 75 cents per mile. And so we see that this is a real problem that people face every day. In order to solve this problem, once again, as I said, we'll have to consider the length of the route, which would be the determining factor to how much the entire route costs for the red line and for the blue line. So how do we do this? Let's just make a small illustration, just a random curve. And let's just say we decided to say, hey, let's just put a ruler from the beginning point to end point. And we just measured it straight. Now, there's nothing wrong with that, but we'll see what happens when we do that. And we'll also do another method where we actually choose about 4 segments to approximate the curve. So we have n equals 1, n equals 4, and n equals to infinity. Now, the n is the number of segments that we use to measure the curve. Now, you'll see why we choose a different number of segments to measure the curve. And while we're on this subject, when I have n equals 1, n equals 4, n equals to infinity, those are what we call cases. So for first case, we have 9.2, 9.8, and 10.53521. Sorry. And those are all miles. So when we have n equals to infinity, that's actually the value of the curve. So we have zero error when we have infinity number of segments. So it's kind of hard to imagine right now. So to help us along, we'll just label the points along the curve, and we'll start to build upon what we can use to conceptualize this infinity number. So first of all, we have x minus 1 minus x not equals the change of x1, or delta x1, which is a Greek symbol. And on the second line, we have the first segment, which is x1 equals the square root of x1 minus x naught squared minus y1 minus y naught squared. And that is the distance formula. If you don't know it, it's a very popular formula to use in engineering and mathematics. And we just interchange that with the first equation that we have on the page, which is this delta. And delta, of course, as I said again, is just a change. So it's a change from the x1 to x naught and from y1 to y naught. And the reason, if you don't know why we use the square, is to make sure that if we have a negative value, it doesn't really alter the result. And so that the negative value and the positive values are all considered the same. So as we see here, we can have multiple segments. And so along that curve, the total is going to be equal to the S1, S2, or the number of the total length of the segments added together, which would equal to S total. So we have S total is, you see that squiggly line? That means that it's approximate. It doesn't mean that it's equal, but it's near the value. So we have a summation of all these different segments, and that's shown in the sigma sign, which is another Greek symbol, from 1, the first segment, to the nth segment, which is the last segment. So we just throw in this pretty much the same expression that we had underneath the square root. Then we start to develop this a little more, and for the equation that we're on right now, we use a little trick. We need to do a substitution. We call it factoring out. So we factor out a term, and we have delta xi squared that's being factored out. And you'll see why we do this later on. But one of the key, stepping stones you can use in mathematics is factoring out, because once you do that, you can separate things. Once you separate, it's like divide and conquer. It makes it a lot easier to deal with the individual parts rather than the whole sum put together. So if you can break things apart, always go that route. It's going to make your problem solving a lot easier. And as you can see here, we had delta xi squared underneath the square root, and we just have that pushed out now, and now it's just delta xi. And so we have s total is equal to the limit as n goes to infinity. Now, this is the key step that we make, because as n goes to infinity means that we have an infinite amount of segments. You remember that case where we had the miles equal to 10.521? This is the case that we're working on now. Before, we were working on something less, like n equals 8 or n equals 9 or some kind of countable number. This is not countable. And this is when we enter the realm of calculus and differential calculus. So as we go on, we develop this a little bit more. We introduce a mathematical construct called the integral. So we need to integrate from A to B. And so we also introduce a dy over dx, or dy of dx. And what this is essentially the integral or the calculus version, differential calculus version of delta. As we said, delta is more countable, like 1, 2, 3, 4, 5, and dy dx is not countable. It's a mathematical construct. So we do another substitution. We have y equals to f of x. And so from this point, we can just plug in y equals to f of x into dy dx, and we have a new form. And so what this says is that you can have any formula, and all you have to do is plug in that formula into this equation that we have here, and it will give you the length of the curve or the length of the arc. So this is what we call the arc length formula. It's very helpful in calculating the length of the curve, and it's pretty much the only way you can use, besides some approximation methods, to really hone in on what is the length of the curve. And that's what we need to in order to solve our problem, as far as what's the most cost-effective route. Through this problem, we had a few key substitutions. The first one was the factoring. Oh, not the first one, but one of them was factoring out the term delta xi squared. Another one was setting the delta, which is x1 minus x naught. Another one, of course, was y equals f of x, which is very important to know. It's just a fundamental function that we use throughout mathematics. And we have two more, jumping from the incremental form to the differential form using the limit, and the introduction of your operand, the integral. So that was pretty much it. I hope this was a little bit helpful in guiding you into understanding what the purpose of calculus is and how it can be useful. You might not come across this in your mathematics course, but please do remember this build up from the differential form or differentiations to integral calculus